The Kavli Foundation supports science and has established prizes in 3 areas: astrophysics, nanoscience, and neuroscience. From the largest to the smallest to the most complex.
We will be using these gravitational waves for, most excitingly, most interestingly, is to explore in great detail the first 1 second of the life of the universe.
The CRISPR technology is just very exciting because it's going to enable a lot of science to be done that was impossible to do in the past.
We can drive the brain at any point in life to a healthier, stronger, more powerful state or condition.
Could there be life elsewhere in the universe?
How does our brain change with learning and experience?
Do we know enough about the human genome to understand the impact of making changes to it?
It was clear to me that if these waves could be detected, it would revolutionize our understanding of the universe.
I've been able to use a nervous system that we understand very well to ask new questions that no one is able to ask in other systems.
What drives me is curiosity.
The thing that's amazing is that there's always more to be discovered.
The World Science Festival and the Norwegian Academy of Science and Letters present the announcement of the 2020 Kavli Prize laureates. Here's your host, Brian Greene.
Hey everyone, good morning and thank you for joining us. I first met Fred Kavli about 20 years ago in Santa Barbara, and I was so taken by his deep curiosity and his generosity of spirit that when Fred suggested that we at the World Science Festival collaborate with the Norwegian Academy of Science and Letters on the announcement of the prizes, I was thrilled, I was honored. And we at the festival have been participating in that announcement since the inception of the prizes back in 2008. Now, with the global pandemic, the way we're going to go about making that announcement has changed. But what hasn't changed is the importance of the prizes and, of course, the great excitement surrounding the announcement of the recipients. In about 15 minutes, we are going to go to Oslo, Norway for that announcement. But first, here's some background on the Kavli prizes themselves.
Who are we? How did we get here? What makes us who we are? And somewhere out there in this vast universe, are there more people like us? These are among the most fundamental questions of human existence, the eternal questions. And they have been at the core of philosophical, religious, and scientific inquiry since the beginning of recorded history. And in rural Norway, those questions were the subject of a lifelong fascination for one particular boy.
I ponder the universe so big beyond imagination, yet composed of particles so small, beyond comprehension, and those little creatures that have taken command of the planet Earth, not because of their strength, not because of their longevity, but because of their brain.
Fred Kavli left his native Norway for North America to pursue his interests in science, technology, and business. He founded Kavlico in 1958 and built it into one of the largest suppliers of sensors for aeronautics, automobile, and industrial applications. But his fascination with the great questions never abated, and he was determined to help scientists find the answers.
The Kavli Foundation supports science and has established prizes in 3 areas: astrophysics, nanoscience, and neuroscience. From the largest to the smallest to the most complex. I believe these prizes are in the most exciting fields of the 21st century and beyond.
The Kavli Prize is a partnership among the Kavli Foundation, the Norwegian Academy of Science and Letters, and the Norwegian Ministry of Education and Research. Every 2 years, the Academy receives nominations from equivalent scientific organizations in China, France, Germany, the United Kingdom, and the United States. Committees of scientists from around the world then gather here at the Academy to evaluate the nominations. After careful consideration and much discussion, those committees select the laureates.
The Norwegian Academy of Science and Letters awards the 2016 Kavli Prize in.
The laureates are announced by the Norwegian Academy through a live feed to the World Science Festival in New York, where top international scientists gather every spring.
The World Science Festival and the Kavli Prize both launched in 2008, and we've had a fabulous partnership ever since. Both organizations are deeply committed to celebrating the great breakthroughs in science and the great scientists of our age.
The laureates represent a mix of career stages. Some are being recognized for a long and illustrious career, while others are very much in the middle of their careers but have nonetheless made significant contributions to scientific knowledge, and the prize is given to encourage further contributions. The September following the announcement, the laureates are invited to Oslo to receive their prizes at a gala presided over by Norway's king or a member of the Norwegian royal family. Each of the 3 categories carries a $1 million cash prize, and each recipient is awarded a gold medal.
Let these prizes be a token of thanks and gratitude for moving us along the path of greater understanding of the human being, nature, and the universe.
The eternal questions of the universe in the biggest, smallest, and most complex areas of science. One step closer to being answered because of the scientists whose names are about to be revealed.
In just a few minutes, we are going to go to Oslo, where the president of the Norwegian Academy of Science and Letters will announce the newest Kavli Prize laureates, honoring game-changing scientists whose discoveries impact our lives. But how has the prize impacted their lives? To find out, we spoke to some recent recipients. Here, take a look.
I'm Carla Schatz, and I'm a professor of neurobiology and biology at Stanford University. I won the Kavli Prize in neuroscience. I won it for my studies and discovery that the baby's brain, even before birth, it's already training itself for experiences after birth.
My name is Irene van Dishoek, and I won the 2018 Kavli Prize for Astrophysics for my work on molecular astrophysics, how are molecules formed in space, and what is their role during the formation of new stars and planets. This work is important because it tells us about our origins.
I received the 2018 Kavli Prize with my colleague Emmanuel Charpentier for our work to develop the CRISPR-Cas9 genome editing technology. It's a tool for scientists to rewrite the DNA in cells and organisms, and it's given scientists worldwide a powerful way to control the genetic information in all living things. So winning the Kavli Prize gave me a lot of opportunities to pursue science in new directions, and currently I'm working to develop both a rapid testing strategy so that we can test people that might be infected with the coronavirus that causes COVID-19.
What we've learned about the way the baby brain develops can actually have some relevance for the aging brain and Alzheimer's disease. And, I would say that our lab, again, we don't belong in this field of Alzheimer's disease. And in other words, that's not where we normally work. And I think, when you have the kind of special recognition that a major prize can give you, you also have confidence to at least give it a go and try something completely new and different.
Yes, it certainly has had an impact also on my research, not in the least because it attracted quite a number of very bright young students that wanted to work in our group, and that's always the motor of research, having the brightest young people.
It also validates the amazing contributions of all of my students, and that is probably the most meaningful thing to me.
My advice to the new 2020 laureates: enjoy this day and the ceremony to the fullest. It's a wonderful experience. It opens so many doors.
Celebrate with your friends and families, and especially with the incredible young scientists that have contributed to the discovery that you're being recognized for.
My advice to future laureates of the Kavli Prize is to use the publicity of the prize and the recognition of science in general to inspire future generations, and also to inspire our own colleagues to think outside the box, to try risky experiments, and to use our talents wherever they're needed to address problems in the world.
The 2020 Kavli Prize recipients will be announced in just a few more minutes. But when you think about the thousands of creative, insightful scientists around the world, how can you possibly narrow it down to just one scientist or one group? Well, my next two guests were charged with doing precisely that. Andrea Ghez was on the committee that chose this year's laureate in astrophysics, and Susan Coppersmith was on the committee for nanoscience. Thank you both for joining us. I'd like to begin with Andrea. You know, it is a very difficult thing to make these decisions who will be the recipient of a prize. And I wonder, what impact does being entrusted with that responsibility have on you?
Well, it forces you to take the job very seriously and to think very thoughtfully about two things. One is what's going on in the field. And the other thing is, what does the Kavli Foundation want to accomplish with this incredible recognition?
And what do you think it is? I mean, what is, in your mind, what's the value of prizes in science? And in particular, what is the purpose in your mind of the Kavli Prize?
Well, after going through this process and having thought about it in a way that I hadn't thought so carefully about before, I really have come to understand that while prizes are wonderful in terms of their the ability to showcase what that person has done, it also bestows on that person incredible responsibility. I mean, you're both showcasing some really exciting science, where the field is, but you're also asking that person to shoulder the responsibility of sharing what it means to be a scientist, what are the opportunities in the future. So it's more complicated than I had ever really had the chance to think through. So I have to say, I really enjoyed the opportunity to sit on a committee like this, where you're doing the very hard work of looking at a huge number of people who are incredibly deserving.
Susan, I know you probably can't reveal the inner workings of the prize committee deliberations, but can you give us a sense of the process by which the Kavli recipients are chosen?
So, as Andrea said, there are very, very many nominations, and reading the nominations is very humbling, and it's incredible how much, really incredible work is going on. Then you go to Oslo in December, and there's a meeting where basically you try to boil it down to which are the nominations that you're going to really investigate. And basically we were assigned things that, we got enthusiastic about and said, well, okay, we'll start putting together the case for these people. And then there's a series of conference calls, emails, going back and forth. And it's done in that legal kind of way where it's done through, various nominations are developed, and then and you get invested in your people, and yet you have to come to a consensus. And that coming to a consensus, I think, really helps to, say, well, this is a group that, the whole committee really feels is appropriate.
Now, each of you were on different committees, if I understand correctly. Do each of you know who the other committee chose?
No.
You do not. Well, here's the thing. You are about to find out. We're now going to head to Oslo, Norway, where the committees entrusted with choosing the 2020 Kavli Prize laureates are ready to announce their decisions. $1 million, a gold medal, and a singular distinction.
Ladies and gentlemen, this is a great day for science, and particularly for excellence in science. Welcome to the Norwegian Academy of Science and Letters, and to the announcement of the Kavli Prize for 2020. Today we're honoring groundbreaking work in 3 scientific fields, work that has provided us with brilliant new knowledge, insight and ways of thinking about astrophysics, nanoscience and neuroscience, or in the words of the founder of the Kavli Prize, Fred Kavli, the largest, the smallest, and the most complex. Without any delay, let us go straight to the new winners. And so we begin with the smallest, nanoscience. For sub-angstrom resolution imaging and chemical analysis using electron beams, the Norwegian Academy of Science and Letters awards the 2020 Kavli Prize in Nanoscience to Harald Rose, Maximilian Haider, Knut Urban, and Andrei Krevanik. And to elaborate our choice, allow me to introduce the chair of the Nanoscience Committee, Professor Bodil Holst.
Seeing is the first step in scientific advancement, understanding, and engineering. The 2020 Kavli Nanoscience Prize honors 4 pioneers who enabled humanity to see the structure and chemical magnification of materials in 3 dimensions at unparalleled high magnification. A major goal of nanoscience is to create materials and devices assembled with atomic scale precision so we can invent new functions and techniques. The size of an atom is around 1 angstrom. That is 100 millionth of a centimeter. Imaging and analysis of materials and devices at the sub-angstrom scale is crucial to see how they might work. The resolution of a classical microscope is limited by the wavelength of what is being shown as an object. Visible light has a wavelength around 5,000 times larger than an atom's, which means that optical lenses cannot image atoms. In the early part of the 20th century, beams of electrons with atomic scale wavelengths were invented, leading to the development of the electron microscope in 1931. However, making ideal lenses for electrons turns out to be a big theoretical and experimental headache, because lens aberrations limit the resolution. For more than 60 years, people struggled. Through persistence, ingenuity, and by embracing new computational power developed in the 1990s, This year's Kavli laureates constructed aberration-corrected lenses and made sub-angstrom imaging and chemical analysis in 3 dimensions a standard characterization method. 3 of the laureates co-founded 2 companies and commercialized their lenses, contributed further to the major impact of their scientific work. Since then, their microscopes have played an enormous role both in fundamental science and technology, where they are used, among others, by the semiconductor, pharmaceutical, and automotive industries. The 2020 Kavli laureates in nanoscience are Harald Rose for proposing a novel lens design, the Rose corrector, enabling aberration correction in transmission electron microscopy that can be applied to both conventional and scanning microscopes. Maximilian Haider for the realization of the first sextupole corrector based on Rose's design, and along with Knut Urban for their joint roles in the implementation of the first aberration-corrected conventional transmission electron microscope. And finally, Andrei Krivanek for the realization of the first aberration-corrected scanning transmission electron microscope with sub-angstrom resolution, particularly suited for spatially resolved chemical analysis via the use of a quadrupole-octupole corrector. Congratulations to all 4 winners for enabling us to see further than ever before.
Thank you, Professor Holst. And now from the smallest to the very largest, astrophysics. For his groundbreaking research in the field of observational X-ray astronomy, covering a huge range of topics, from gas flows in clusters of galaxies to supermassive black holes at the heart of galaxies, the Norwegian Academy of Science and Letters awards the 2020 Kavli Prize in Astrophysics to Andrew Fabian. Please let me introduce the chair of the Astrophysics Committee, Professor Viggo Hansten.
X-ray astronomy has granted us access to the extremely hot and energetic components of the universe. In the current cosmological paradigm, the universe is a living ecosystem in which gas flows into galaxies and the black holes at their centers and the subsequent release of energy back into the galaxies and their local neighborhoods all play vital roles. X-ray observations have provided stunning evidence for these processes at work, revealing how the major constituents of such a galactic ecosystem can profoundly influence their overall evolution. Andrew Fabian is one of the most prolific and influential astronomers of our time, and has been a leading figure in several major areas in X-ray astronomy. On small spatial scales, the size of a solar system or even smaller, spanning light minutes or at most light hours, he predicted and co-discovered high-velocity X-ray spectral emission from around black holes. This allowed Fabian and his collaborators to develop a powerful method for measuring their spin. These spinning black holes may provide the energy to heat the intergalactic gas and affect the evolution of constituent galaxies. On larger spatial scales, spanning millions of light years, Fabian played a vital role in revealing the mystery of, and the solution to, the prodigious heating and cooling mechanisms operating on intergalactic gas in clusters of galaxies. Andrew Fabian's breadth of knowledge and insights on vastly different universal scales have provided key physical understanding of how these disparate phenomena are interconnected, and we thank him for his cosmologically important work.
Thank you, Professor Hansten. And now from the largest to the most complex, neuroscience. for their transformative discovery of receptors of temperature and pressure, the Norwegian Academy of Science and Letters awards the 2020 Kavli Prize in Neuroscience to David Julius and Adam Pataputian. To expand upon our choice, let me introduce the chair of the Neuroscience Committee, Professor Kristine Beate Valhovd.
If you are sitting comfortably and the temperature in the room is just right, then you shouldn't even notice. But if someone turns the heat up or down dramatically or gives you a show, you'll definitely react. Sensing temperature and pressure are critical to adjust to our environments, yet the neural mechanisms for how these features are detected by our nervous system have been mysterious. The research of David Julius, both literally and figuratively speaking, is hot. In a series of intriguing experiments, Julius used spices to understand mechanisms of temperature and pain sensation. Julius discovered the receptor for capsaicin, the compound in chilies that gives us the sensation of heat. And this led to the identification of the first biological temperature sensor. TRPV1 is an ion channel that opens up on the surface of cells at certain temperatures, thus contributing to our ability to detect temperatures in the warm to hot range. Julius also found that TRPV1 is activated during tissue damage and inflammation, enabling integration of both temperature sensing and inflammatory signals. Next, Julius, and now also Ardem Pataputian, turned to how colder temperatures are sensed. They found another TRP channel that responds specifically to lower temperatures by using plants that produce cooling agents, such as menthol and peppermint. Julius found that some of the TRP channels are mutated in familial pain syndromes and even act as targets of spider and scorpion toxins. New strategies for treating chronic pain are greatly needed, and TRP channels are now targets for the development of new pain relief drugs. Along with temperature sensing, touch has long been a slippery sense. We can detect indentations on our skin 1,000 times thinner than a human hair. How information about such physical stimuli is communicated in our nervous systems has been a long-standing problem in neuroscience. Ardem Pataputian has unraveled fundamentals of our sense of pressure and touch. He and his team discovered proteins that are pressure-sensitive mechanical sensors, the piezo's. Pataputian analyzed the molecular and functional properties of piezos and revealed that they are directly responsible for pressure sensing in the skin. He showed that piezos have critical roles also in proprioception, that is, the sense of awareness of our bodies and movement. This effect being demonstrated by lack of coordination in both mice and humans deficient of piezo2. He also revealed the role of piezos in interoception, the sense of internal organs, such as via pressure sensing in the lungs and blood vessels. Piezo mutations underlie a broad range of genetic disorders, and their discovery opened the door to understanding mechanobiology in health and disease. Together, the discoveries of David Julius and Ardem Pataputian revolutionized neuroscience by providing a molecular and neural basis for both thermosensation and mechanosensation, and these discoveries formed the foundations for the development of new treatments. Congratulations.
Thank you, Professor Valhovd. And congratulations to all our laureates. You've made great contributions to science, providing us with knowledge that will reach and have effects far beyond your fields of investigation. Your work stands out as truly excellent, and it will inspire future generations to use their talents to pursue knowledge. Our culture is built upon science, and it's a privilege to honor those who contribute the very best. Before we finish today, a word from the Norwegian Minister of Research and Higher Education, Henrik Asheim.
First of all, congratulations to the Kavli Prize laureates of 2020. The Norwegian government is proud to be one of the 3 Kavli Prize partners. Thanks to your pioneering work, we know more about the mysteries in our universe, from the largest to the smallest and most complex. We have once more been reminded how important science is to overcome difficult challenges, and how much further we can come by working together. Your scientific contribution moves the world forward. So please keep uncovering the mysteries of the universe, keep up the excellent work, and again, congratulations.
Thank you, Minister. And so we bring these announcements to a close. We look forward to welcoming you to Oslo to celebrate these laureates. Due to the pandemic, we are postponing the awards ceremony for today's prizes, but we'll double down and celebrate both the 2020 and the 2022 Kavli laureates together in Oslo. A warm welcome to Norway in 2022.
Well, there you have it. 7 scientists in 3 fields whose discoveries have been so exciting and so innovative that they've been singled out for one of the most prestigious prizes in all of science. And we're going to talk to several of the recipients right here, right now. Andrew Fabian is the recipient of the 2020 Kavli Prize in Astrophysics for his groundbreaking discoveries in observational X-ray astronomy. Andrew, congratulations on being the recipient of the 2020 Kavli Prize in Astrophysics, a wonderful honor. And of course, thank you for joining us. So Andrew, you know, many describe the universe as this vast expanse of silence. But as I understand it, your work and your view is that it's not as silent as perhaps we once thought. What do you mean by that?
What I mean is that when we look at the gas between galaxies, which is extremely tenuous, you can nevertheless get organized motions of it. You can get pressure waves, which are sound waves propagating through. And it's possible that there is considerable amounts of energy moving around in the sound waves in the clusters of galaxies. And we've found possible evidence for this in some of our X-ray images. And I would stress that when I say sound waves, I'm talking about very low frequency sound waves, well beyond our range of hearing. When we talk about sound waves that we hear, we're talking about hundreds of cycles per second. And I'm talking about 1 cycle per 10 million years.
So it's a music of the spheres, but you have to have a lot of patience to hear it.
Or very big ears.
Very big ears, absolutely. When I was a student, I did a project in radio astronomy. And my advisor, I was speaking to him one day, and he told me that he'd been doing some soul searching. He was going to really radically shift his career. And I said, oh, what are you going to do? And he says, I'm going to shift from radio astronomy to millimeter astronomy. And so I always have wondered, how is it that one picks the frequency of light that one's going to focus their attention on? It seems to be a very substantial career choice in trying to decide where in the electromagnetic spectrum to focus your attention.
Yeah, with me, it was, by chance. And I've tended to work in the X-ray band, looking at X-rays, but I also make use of optical telescopes, infrared telescopes, radio telescopes. So I'm prompted mostly by what I see in the X-ray band, but nowadays you've got to take all wavelengths into account to get a full picture of what you're studying.
Your work has focused in a wide range of areas in astrophysics, but you've received the prize for the work you've done in X-ray astronomy. Now, many people in the general public, they hear about X-rays, they think about it as a means to look inside of something. Can you just give us a sense, how do X-rays play a role in astrophysics?
Okay, X-rays are a kind of light. It's just the frequency is 1,000 times higher than that of visible light. And so if you go out and look at the night sky yourself, you see the visible light sky. But if you look with an X-ray telescope, you'll look at frequencies 1,000 times higher, and you're looking at objects typically that are 1,000 times hotter, which means we're looking at things that are millions to billions of degrees in temperature rather than the thousands to tens of thousands of degrees of stars. and galaxies. So what we're doing mainly is looking at dead objects in the universe like black holes, neutron stars, white dwarfs and things, and as well as vast seas of very hot gas in the atmosphere, in the universe. In the universe, there's gas between galaxies that gets squeezed up when galaxies cluster together, and they become very strong X-ray sources. And I've been looking at the interaction between black holes in the centers of these clusters and in the cluster atmospheres, trying to understand how the energy from the black hole gets transmitted out into the surrounding gas.
And what are the sizes, just to give people a sense, what are the masses of the black holes that you study with X-ray astronomy?
Well, we look at stellar mass black holes, which have got masses from, say, 5 to 25 solar masses. That's 25 times the mass of the sun. Most of the ones we look at are active galaxies or quasars, and their masses are from 1 million to 10 billion times the mass of the sun. So we're looking at that kind of range of mass of black holes, and they are the black holes that we know about in the universe.
And what do you say to people who bring up the issue? They say, hey, there's so many problems in the world today, poverty, refugee crises, global pandemics. Why should we put funding and effort into a seemingly esoteric subject like studying black holes and studying the cosmos as opposed to focusing on the real world challenges that face us right now?
I think I would explain it as what we need to do is stimulate the next generations of scientists. We need to get more people interested in science. I think the current COVID pandemic demonstrates the problem with people in charge who don't understand science. And we've got to propagate the scientific method. And one way to get people to do that is to get them interested in science. And it's quite easy to get members of the public, young children, students, interested and excited in astronomy.
And when it comes to young students, many of whom no doubt are watching this right now, is there any advice that you give to the excited young science student that wants to pursue a career in astronomy or astrophysics?
I think what I would tell them that astronomy is very exciting. I would say that, and you can tell this by looking at newspapers and the media, that almost once a month there's something new discovered in astronomy. So there's lots going on. It's a very big universe, and you could be the first person to look at a certain galaxy, and you may be the one who discovers something special from it. And what I would also advise them is to make sure they've got a good grounding in physics and mathematics before starting off.
Yeah, absolutely. So Andrew, thank you again for joining us, and congratulations on receiving the Kavli Prize, a wonderful honor, and best of luck going forward.
Thanks very much, Brian.
I now have the honor of introducing the newly named Kavli laureates in neuroscience, David Julius and Ardem Pataputian. Gentlemen, welcome both to this conversation, and congratulations to each of you on this spectacular achievement, being the recipient of the 2020 Kavli Prize. Just want to start with Ardem. You know, I'm fond of telling people that you never actually touch anything, right? When you grab hold of a glass, it's the electrons in your hand that are pushing against the electrons in the glass, and there's a separation between them, even though it feels that you have direct contact. Sort of, that's my physics description of what the sense of touch is. As I understand it, you've gone like infinitely farther than that weak description at this intersection of both physics and chemistry, giving us insight into the nature of touch. Can you tell us about the work that you did that won the Kavli Prize?
Absolutely. Nice meeting you, Brian. It is really a great honor. And so our work is really started with the sense of touch. And indeed, sense of touch does something pretty amazing, which is translates this physical force, pressure and temperature, into a language that cells understand and communicate with each other. In this case, either a chemical signal or electrical. So we know a lot about how hormones, neurotransmitters talk to each other in cells, but we knew very little about how physical forces are communicated. So David's work and my work has focused on this, and we find in a way the biological sensors that take this physical force and translate it into chemical.
So do you imagine that one day being able to use these insights to manipulate the way that we engage with the world, the kind of sensations that we have being brought under a more volitional control as opposed to just the random stimulation that we receive from the environment?
Absolutely. With respect to, I was talking to someone who studies virtual reality in the form of video games and such, and they're saying that the tactile version of this is the least understood, and we have vibration, but that's about it. So I think the whole engineering aspect of tactile science to the biological understanding might indeed come together someday.
And so, David, your work, as I understand it, is in the related area, but you focus more on our sensations of heat and cold, how we respond to various chemical irritants. Is that accurate? And what has been the dominant focus of your research?
Yeah, that's accurate. It really sort of extends from our initial use of natural products to identify molecules that are involved in touch sensation, and really pain sensation is sort of what's driven a lot of components of our work over the years. And a fascination of using natural products. It's really a great interface between anthropology, chemistry, and neuroscience, understanding how we experience our world through natural products and how they can help us reveal endogenous systems within our own body that are involved in important physiological processes. And
what sort of natural products? Just to give me a sense, what sort of natural products?
Like capsaicin, which is the main pungent agent in chili peppers, menthol, which is the cooling agent in mint leaves, these other sort of funky compounds called isothiocyanates and thiosulfonates, which are the things in wasabi and onions and garlic that elicit a sensation of irritancy, I guess you would say, and trying to understand why and how all these activate neurons and molecules in our body that generate a sense of pain and awareness of that.
Ardem and David, both of you have dealt with and are dealing with molecules that communicate the sensation of pain, that transport that sensation in the body. In the best of all worlds, what do you think you might achieve with that going forward?
Absolutely. I think if you look at pain treatments, many assume that this is kind of a solved problem, but nothing can be further from the truth. There's some conditions such as neuropathic pain where there is very little out there that helps patients. And when there are drugs, they have some serious side effects of addiction. I'm sure you've all heard of the opioid epidemic now. And so we do need separate, different classes of molecules that can help treat pain. And what David and I study, the peripheral nervous system, is a perfect example of hitting molecules, for example, that are not in the brain. So targeting them would not have any of the downsides of affecting addiction, etc.
The molecules that we've identified are important for us in acute sensation, that is our ability to detect pain when it's useful and protective. But one of the other great aspects of our work is that it tells us about how these molecules are involved in pain that's not so protective, like chronic pain, when it becomes more debilitating and not as useful as a warning system. One of the big goals is to really use this information to develop a new spectrum of analgesic medicines that can be used in adjunct to or in replacement for current pain drugs.
As science faculty, we all teach students, and I think one of the most important things for students to realize is that even the most highly accomplished scientists, as you both are, have had moments of doubt, moments when things weren't going as well as they would have hoped. Do you have any moments of that you'd be willing to share? Because I think it's valuable, if you do, for students to hear that.
Yeah, I think it's important for students to know that almost everybody in their careers, except for a blessed few, have had times when, long valleys when they're looking for peaks. Most of what we do is failure. A small part of it is success. And there's most of the things that you try in the beginning don't work. I think it's important for students to know that everybody has their moments of excitement that can be brief, sometimes extended, but a lot of the times you're just sort of trying to be patient and work through a lot of problems and get to where you need to get.
Yeah, I can second that. Actually, during the same period postdoctoral fellowship, I had some serious doubts, thinking, I'm working super hard, not getting too much interesting data, and not making any money, and I started looking into other lines of science-related work, such as consulting and things like that. But I'm so glad decided to stick with science, because I think it's the best job in the world to be a professor. You go into lab and work with brilliant young trainees to explore the mysteries of the universe. And then once in a while, without you applying, someone nominates you and you get an award like Kavli. What else can you ask for?
Exactly. Well, it's been fascinating to speak with both of you. Congratulations on the award, and more important than that, the best of luck and continued success in going forward in research that has the potential to really impact the way we live. So great to meet you both. Thanks for joining us.
Thank you.
Thank you so much.
My next two guests study the nano world, and their discoveries have made them giants in their field. Harold Rose and Andrei Kravanek are recipients of the 2020 Kavli Prize in Nanoscience. Harold, let me begin with you. The electron microscope, it's been around for decades, but my understanding is that there was a flaw. And can you tell us what that flaw was and what you did to fix it?
Electron lenses you have in electron microscope, they are compared to light optic lenses, they are very poor. And in order to make them better, you need glasses. And so I designed glasses and bought these poor lenses. However, the entire system was not stable enough. You wiggle around and don't see a sharp image.
I see. So in essence, you sort of put the arms on the glasses. If we were to wear glasses that didn't have arms that hooked onto our ears, the lenses would move, and you found a version of that idea to apply to the electron microscope.
Yeah.
So Andre, can you give us a sense of where the state of resolution was before your work and where you took it by virtue of your discoveries?
It's often said that electron microscopy is the eyes of science. And that's very true. It's a scientific method for letting us see what's happening at the fundamental level of matter, at the level of the atoms. And before we could not see the atoms very clearly, after we could.
And so can you give us a feel, Harold, for the kinds of scales that we're talking about? How small can you see, so to speak, with the corrected electron microscope?
Think of a golf ball. What a golf ball is? It's about the diameter of an inch. And now think of the Earth. Now the ratio of the golf ball to the Earth is the same as the ratio of the atom to the golf ball.
So Andre, can you give us a sense when we talk about looking at an atom with these devices that you and Harold have pushed to the next level, how close do we actually come to seeing an atom?
Well, you see atoms. You can put an electron beam on pretty much a single atom, and you can ask it, what kind of an atom are you? And it will respond. It will give you an energy loss spectrum in which it identifies itself. And not only that, it also tells you how it's bonded to its neighbors. So if you have, say, a silicon atom which is bonded to 3 neighbors and a silicon atom which is bonded to 4 neighbors, it gives you a different signature. So it's hugely revealing.
So with that kind of resolution, which is so incredibly impressive, what do you imagine might be the applications, perhaps even the practical applications of this capacity to observe the microworld with such fidelity?
There are many situations where a single atom will make a difference. In all the wonderful modern electronics, it's based on metal oxide semiconductor field effect transistors. MOSFETs for short. And if you get one atom in the wrong place at that interface between the metal and the oxide, it will destroy the properties of the transistor, and your iPhone will not work so well.
So a question to both of you. En route to great discoveries, there are many examples in the history of science where there's resistance from the mainstream community. The example that comes to mind for me, when Einstein was going to try to figure out the force of gravity, Max Planck said to him, "You shouldn't do it. You're not going to succeed. No one's going to believe you." But Einstein persevered. In each of your cases, did you feel that there were moments where the establishment was not behind you, not encouraging you, trying to steer you into a different direction?
My wife tells me that I'm rather stubborn. And my stubbornness was one reason, because you see, it's, everybody said you will fail. Yeah, but there was no physical reason for it, because it was just a matter of a lack of necessary technology. And so my feeling was, I have to wait and until technology will be available, and then it will work. Real advancement in science needs good ideas, endurance, devotion, and nowadays perhaps teamwork.
Andre, any words for young scientists or funding agencies that you want to leave us with?
When I decided to go into aberration correction, 4 professors would tell me, "You bearing your career, this is never going to work." And one had to have a healthy dose of self-confidence to disregard it. And also, I was at the stage in my career where I thought, well, if it doesn't work, I will have given up 2 years of my life. But I've done lots of other worthwhile things before. People will not hold it against me. So this was a project where I went into it thinking, most people expect me to fail. I can only exceed expectations. So my advice would be, try to find a really interesting project like that at the right stage in your career. Don't do it right in the beginning. If I did that for my PhD and the project failed, there would have been no PhD. There would have been no success career to follow. But there is a stage where you can afford to do things like that. So don't be afraid. Go after it if it looks exceptionally promising, even though the outcome is not very certain.
Well, great advice. And of course, we are thrilled that both you and Harold did succeed. So congratulations on your achievements. Congratulations on this wonderful award from the Kavli Prize 2020 Nanoscience. And thank you both very much for joining us.
Thank you very much.
All right, that is it for today. I'd like to congratulate all the newly minted Kavli Prize laureates on this great honor, and to wish them all continued success in their search for answers to the biggest, the smallest, and the most complex mysteries of science. My thanks to the Norwegian Academy of Science and Letters, the Norwegian Ministry of Education and Research, and the Kavli Foundation. I'd also like to thank all of you for joining us here today, and to welcome you to the next Kavli Prize laureate announcement, which will take place in 2022 in New York City at the World Science Festival, where we anticipate celebrating together and in person. Until then, you can follow the World Science Festival on its various channels on YouTube, Twitter, and Facebook. I am Brian Greene. Take care.